We've talked about energy transfer in latent energy and phase changes, and we've talked about it in conduction and convection. We're going to talk about it now for radiant energy, and that process of energy transfer of radiant energy is called radiation. It's one of the most important energy transfer processes in atmospheric science because it transports energy in empty space. So it can take energy from the vacuum of space around the sun and move it through to our globe, and that's how we stay warm. So that's how important that energy is, and let's explore it now. In talking about that, we can go back to our old analogies, and remember we said that radiant energy transfer is like sending a text to your friend. Another way of looking at this is to look at the beach analogy that we've used before, that the sun feeling hot on your skin is radiant energy transfer. So that when we talk about this, when we talk about the laws again of radiation, all of these laws are about emission from the sun. They're all about emissions. So for instance, everything radiates at all times, 24/7. You, me, the desk, the earth, the sun, everything radiates. Second law about emissions is the hotter the object, the shorter the wavelength that is emitted by the object. So that the sun emits very, very short wavelengths. We on Earth emit longer wavelengths. And then the third law about emissions is that as an object's temperature goes up, the total number of emissions goes up. So just to review that, the radiation laws are all about emissions and the type and the amount of emissions. When we look into processes of radiation, let's get into a little bit more specifics. It's kind of an analogy of an airline flight. So emissions are like the takeoff, and transmission is moving the radiation beam through the medium, whether it be a vacuum or whether it be air. That's transmission, kind of the cruising altitude. And then after that, the radiation starts to hit things. First, it hits molecules up in the upper atmosphere and can get scattered. That is a form of reflection. And then it can get scattered a little lower in the atmosphere by clouds or by surfaces like high mountaintops and so forth. It can be reflected off of snow on mountaintops. And then it can be absorbed as well by clouds and by surfaces. So it starts hitting things. It can be scattered, it can be reflected, it can be absorbed. Eventually, after it is absorbed, it's going to be emitted again. So this radiation goes back and forth. In hitting surfaces, let's talk a little bit about the behavior of radiant energy as it hits surfaces. We talk about transmitting through space and the vacuum of space. Well, the Earth's atmosphere is not a vacuum. And when it is transmitting through the Earth's atmosphere, the radiation waves tend to bend, refraction, just a bit, and tend to lose some of their energy in the atmosphere. So that transmission that I note here, it cruises through the medium, it cruises through the atmosphere with a little bit of a reroute, and it loses some fuel. I'm trying to go with that air flight analogy again. Some of the rays can get deflected by or reflected by molecules, and that's called specular reflection. It refers to albedo in your book, or the reflectivity of rays. Another form of deflection is diffuse reflection, scattering, which is why the sky is blue, and we'll go over that in a second. Then in terms of that, let me move this up, we have absorption. that's when the rays land and discharge their passengers and discharge their energy to the object or the surface. And then finally we'll have emission that's like vertical takeoff of a helicopter. I'm not sure what that helicopter is, the name of it. But those are the types and how they interact with surfaces. When we talk about great transmitters in our atmosphere, those include water and glass. Water actually transmits very well in, radiation transmits well in water. That's why when you put a pencil in a glass of water, you'll see the line kind of shift, right? It's refracted by the water, and it will be absorbed by the ocean bottom or the lake bottom. So it'll transmit, lose a bit of its energy, and be absorbed by a bottom. Same thing with glass. It transmits through untreated glass very well, and it's absorbed by furniture or carpets inside. This is a major reason, and the misunderstanding of that reason is a major reason for child deaths in hot cars. Because people say, well, it wasn't that hot outside. They're noticing convection around the outside. There's no convection inside the car. That car is being hit by transmitted radiation. There's no convection. Even if you open up the windows 2 or 3 inches, there's no effective convection in there to move that air around and cool it. That's transmission. And in terms of that specular reflection that we were talking about, that reflection that bounces off the surfaces, what you'll note here is that fresh snow and clouds are very good at reflecting the sun's energy and keeping us cooler. That's why we have to keep the polar ice caps in place, because they do keep us cooler by reflecting the sun. You might think that water reflects really well. Water is a really controversial measurement, and it really impacts our climate change models, because water has qualities that are different for albedo. If you want to study that for a final project, it's a great thing. But we are comparing the waves of water to the waves of radiation, and waves don't go together well. As you see in this list, there's no other waves on this list. Water has its own separate reflective qualities, and they're not well reflected in albedo. Why the sky is blue is not specular radiation, it's not mirrored radiation, it's actually diffuse or scattered radiation. And to just talk to you about that, when you are coming in through the very rare atmosphere up high, the blue visible rays will hit some molecules in the less dense upper atmosphere, and those very small blue and ultraviolet rays will get scattered out very easily. Then there are longer green rays that get scattered out when you have more density to the atmosphere, when you're a little lower in the atmosphere. It can also happen when there's an enormous amount of debris in the atmosphere or humidity in the atmosphere. You often see green skies right before tornadoes. For that reason, they're kicking up dust, and they are scattering the green light. Yellow light, sometimes you see that before a hurricane or a big snowstorm, because the same thing, you're getting a lot of humidity in the air that's scattering the longer yellow waves. The red waves are the longest. They are scattered when they have to go all the way through the sunset sky on a really low angle. So those are scattered last, and they are longest. Now you know why the sky is blue. In terms of absorption, so we've been through transmission, we've been through reflection. In terms of absorption of rays is kind of like the Earth is a pizza crust, and it is now holding a pizza with all the works. So every kind of ray you throw at a perfect absorber will become like gamma rays and UV rays and IR rays and visible rays. It'll take anything on. A perfect absorber will absorb anything, like a great pizza crust for a great pizza. And a perfect emitter will cast off and emit and discharge all different types of rays that it receives. So in other words, what I'm showing here is I'm showing it if you were holding a vacuum and sucking up all of the things on your great pizza, that would be kind of like the great pizza discharging everything that it took in. That's a perfect emitter. It's hard to find examples of perfect emitters, and there are no great examples that I can show to you. There's decent examples. I don't want to confuse you, but what I will say is this, that a black body is known as a perfect absorber. It takes it all in, everything that's hitting it, and it will emit out everything that in the same quantity. When you have more absorption than emission, that will make the temperature of the object go up. Makes sense, right? When you have more emission than absorption, that will make the temperature object go down. And when they even out, like in a black body, the temperature will stay the same over time. An example of a black body, and it's not a good example, is a black road. Now, a black road is sitting on the surface of the earth, and you know it gets so hot during the summer. It is taking in all the visible light and all the IR light that is coming through the atmosphere, and it is absorbing a lot of it and getting very, very hot. This visible light is emitted out a bit and has to do with the mirage that you see there, but most of that mirage is really due to the emission of lower frequency IR waves. Because remember, on Earth, we're not going to get as hot as the sun. We emit lower rays. There are some visible rays that are being emitted there, but it's mostly IR. It's not a great example, but it's a decent one. When the absorption is greater than the emission during the day, although it's still emitting during the day, the temperature of the black road is going to go up. And conversely, at night, the emission is greater than the absorption. There's no sun out, and the emission is greater than the absorption. By dawn, when you head out on that black road, you can walk in your bare feet because that black road is very cool at that point. In fact, it's cooler than the sand next to it because it emits off so efficiently. The Earth's surface would be a black body if our atmosphere did not have greenhouse gases. We'll talk a little bit more about that. So as a result, we're going to get into that a little bit, but the Earth's surface isn't black. And a black body doesn't need to be black, but it doesn't hurt to be black. And the important thing is that a black body absorbs the maximum amount of waves that it can, and it emits the maximum amount that it can. And that's it for this. Let's talk a little bit more about black bodies next.